Okay, students, so what you see in front of you here is the muon detection apparatus. Everything you see in front of you here, when on and operational, allows us to detect muons here at the Earth's surface, which takes into account the expanded lifetime that the muons have when they're created in the upper atmosphere and able to make it all the way down to the surface of the Earth, given time dilation of special relativity that you can read about in the lab manual, or any modern physics book discusses this plight of muons. But in either case, this is an Earth's surface kind of apparatus that allows us to detect muons. So what I thought I would do in this video is show you the bulk components of the muon detection apparatus, and I'll give you just a hint of some of the cables and where the electronics goes and that sort of thing. And in a subsequent video, we'll get into more details about how the signals are processed and all. So what you can see then is essentially two major components to the muon apparatus. This wooden box in the back here, and this NIM crate full of all this lovely electronics here, some of it that you've used before, but this is where all the data is processed. And as the usual suspects, we have an oscilloscope here for looking at the signals, and a trusty laptop in the back there that ends up logging all our data when we start taking the muon experiment. So let me just start with the black box in the back then. So this wooden box in the back houses the scintillation detector that's used to detect the muons. So this detector is not like this detector right here. This detector here is a standard sodium iodide scintillation detector that you've used before for detecting gamma rays in previous labs. So this detector that we see here, this is not what's in the box. What's in the box actually is a large piece of plastic that might very well be about the size of this box. You're sort of maybe in the shape of a pizza box, sort of maybe about that far and about this long and about this thick or so. It's a big piece of plastic, and it is connected on the very end to just the photomultiplier tube here. This brown part here is the photomultiplier. This is the sodium iodide that you've used in other labs. So this photomultiplier is definitely inside this black box. Just this part is then substituted for that large piece of plastic that may be in the shape of a pizza box. So I'll confess that I've never actually seen what's inside this wooden box, but I've seen other replacement scintillation plastic that is used for it. So with that then, there's three cables that go into this black box here. One is this one. This is the high voltage. So because there's a photomultiplier tube here, it has to be biased to the tune of about 1,000 volts so it can do its photon amplification job. This other cable right here is actually connected to an LED inside this box here, and the LED allows us to flashlight artificially near the scintillation plastic for testing purposes, so we don't have to wait for a muon. We can just flash the LED to make sure all the electronics are working. It's sort of an important aspect of getting this experiment up and running. And lastly is this cable right here, and this is the signal that comes from the photomultiplier tube. So really nothing too unusual in what's inside this box here. There's a photomultiplier tube that needs high voltage. There's a signal that comes from the photomultiplier tube. And the odd thing is this LED, which is placed near the scintillation plastic to make false events so we don't have to wait for muons to arrive to see if our experiment is working properly. Okay, so let me just move this out of the way and continue then. So the way we start the experiment in terms of routing the signals and so on is we take the cable here that has the signal on it, and we immediately run that into this little brown box here, which is a preamplifier. So you've used preamplifiers before, and what the preamplifier does has a very high input impedance. So it takes the very, very weak signal that comes from the photomultiplier tube inside of here, very small, and is able to amplify it to some usable levels. So these two things would be sort of connected like this, and that would sort of be our first connection there to get the very weak signal coming from the photomultiplier tube into the preamplifier. That's sort of step one. Okay, so what we do next is kind of clever. The output of the preamplifier, once it does its amplification job, has two outputs on it. This one down here, which isn't used, is the energy one here. So that'll be sort of a voltage that's proportional to the energy of the event in a scintillator. And we're not interested in that in this lab at all. So we're not taking an energy spectrum the way you did with gamma rays in other labs. We're just interested in timing in this case here. So it turns out that the preamplifier on this other input that has this cable connected to it is a timing output. So it's just a pulse, negative going pulse that exists when an event is seen in the detector to mark the time at which it happened. You can look at an oscilloscope. So what we do is actually kind of clever at this point. We take the output of this preamp detector, the timing output of the preamp detector, and we put it into this T here, which does two things. The first thing it does, it sends the signal from the preamp directly into the timing apparatus over here. So you can see that as this BNC-T is connected to something, the signal from the preamp will go right into the device it's connected to. And as I'll show in a second, probably in the next video, that's called the time to amplitude converter, or TAC. So that's one place the signal is routed to. Simultaneously as it's going into the TAC, it's also sent to go around about 10 feet of cable that's just sort of curled up on itself. So this cable isn't going anywhere. It's just about 10 or 20 feet or something like that. It's all wrapped up on itself. And the other end of that goes into the apparatus as well. So you really have sort of two outputs of the timing signal that comes from the preamp. One goes right into the timer, and the other one is delayed because it has to travel through this big loop of cable here. And remember that when electronics travels through cable, it travels at close to the speed of light. So loosely speaking, the signal that comes out of this other line is delayed by the number of nanoseconds that correspond to how many feet we have here. So if we have about 10 or 15 feet or 20 feet of curling in here, the signal that comes out will be delayed by 10, 15, 20 nanoseconds, something like that. So it's just slightly delayed relative to the one that goes right into the apparatus. Okay, so in the next video what I'll do is I'll show you some of this turned on, and we'll start looking at some signals on the oscilloscope.